Hello, and welcome to the video lecture for Chapter 11 from Hewitt Conceptual Physics 12th edition. Here we're going to be discussing the topic of matter, specifically the atomic nature of matter. All right, so you can see there's a lot of topics here, but none of them are particularly heavy or complex topics. It's more of a survey of an introduction to the concepts of matter. You can think of this chapter as a bit of a physicist's point of view on chemistry, but not getting into any of the details and memorization required that would in a full chemistry class. Okay? So first, a quick definition. What is an atom? Well, all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. Okay, so that's kind of a picture of atoms, a nice summary by the physicist Richard Feynman. Okay, so there are a lot of attractive forces between atoms, but they don't want to be too close to each other. Okay, so what's the big idea about atoms, and what's a little bit of a history survey about how we got to our current understanding of the atomic nature of atoms? Well, first thought by Aristotle to be a combination of four elements: earth, air, fire, and water. That was what matter was composed of. It was fundamental. It was magical in a sense. Thought to be composed of atoms by the Greeks from the 5th century BC. So the atom, and the history of that word, is that it was an indivisible piece of matter. So if you split matter enough, like imagine dust, but then you zoom in and split that dust up into finer and finer particles, eventually you reach one piece that's so small that it cannot be split up anymore. It is the indivisible final state. It is the atom. All right? And that's an idea that's really kind of held on by humanity, that is carried through from ancient philosophers to the modern day. Is it accurate? Although, well, not quite. We now understand that matter and energy are related. So in that sense, matter is always divisible. It can always be converted to energy. But the idea of indivisible chunks is kind of the backbone of quantum mechanics, which we'll touch on in a much later chapter. So perhaps they weren't so wrong way back over 2,000 years ago. And of course, the atom itself, as we'll learn in this chapter, and one of the ideas that you will be responsible for from this chapter, is composed of a few key components: the nucleons, which are protons and neutrons, and the electrons. So those are pieces of the atom. So the atom certainly has structure and is divisible. So that part was wrong. And even the nucleons themselves can be split into something called quarks, but perhaps the quarks cannot be split. Perhaps that is the end of the line. Maybe they really are smallest fundamental particles. Okay? So, continuing with the last idea about the atom, it was further proposed as atoms in the 1800s by meteorologist and school teacher John Dalton. All right? So kind of an interesting turning point about where the idea of the atom got some more traction. In 1827, here's a key moment. Robert Brown, a botanist, observed collisions between visible particles and invisible atoms, called Brownian motion. It was a mystery, right? But it took on his name. It was later confirmed by Einstein as evidence for the existence of atoms. All right? These constantly moving particles. Because otherwise it didn't make sense for this botanist. Where was the motion coming from that he observed in the microscope? Why were these tiny little spots of water and imperfections in the water moving? What was causing that vibration? Well, it was collisions with invisible particles that were too small to see with visible light. Okay? Because the atoms are too small to see with visible light. They're much smaller than the wavelength of visible light. Okay? But that is an idea that we'll get to when we talk about light and X-rays and electron microscopes in a later chapter. Okay, but for now, suffice to say, atoms are much smaller than most of our observable techniques in science. Okay, which probably isn't a good idea to think about because it kind of helps you understand why some of these ideas might seem a little wishy-washy. They're not, I mean, they're just, there's more far out than wishy-washy, but it just is a testament to the fact that we have to have some clever ways of observing atoms, since we can't observe them directly. But anyway, based on our modern understanding, what are the characteristics of the atom? They're incredibly tiny. They're going to be on the order of 10 to the negative 10 meters. Okay? That's the size of the atom across. All right? Furthermore, the nucleus, the little center, is on the order of 10 to the negative 12 meters. So 2 orders of magnitude smaller still, a tiny center. And the actual shape of an atom is not perfect elliptical orbits like this. All right? These, by the way, would be electrons. This is just a popular science kind of icon, but not one that is accurate. Okay? And here we have the nucleus. Okay? They are numerous. So if we look at a sample, a macroscopic sample, it is going to have on the order of a trillion atoms. So maybe 10 to the 12 to the 12, maybe 10 to the 24, right? For just a reasonably sized sample. And I mean, that'd be like a small sample, like a pinch of salt might have a trillion atoms. Okay? They are perpetually in motion. They never stop moving. Okay? It is impossible for an atom to stop moving as far as we know. And they're ageless. All right? So the particles that make them, the protons and the neutrons and the electrons that we'll learn about, as far as we know, those particles themselves cannot decay. Now, when they interact with each other, they can change a bit. So, and we'll learn about this again when we learn about radioactivity. So protons can become neutrons, for example. Neutrons can become protons. But that's about it, okay? The proton itself seems to be ageless. It will never go away. And the electron also seems to be ageless. And if they do have a finite lifespan, it is much, perhaps millions of times longer than the current age of the universe at 15 billion years. So for all intents and purposes, ageless. Okay? So which of the following are incorrect statements about the atom? Take a minute, think about your options. All right? Does one of them seem obvious? Yes. They are not manufactured in plants, all right? Nor humans during pregnancy. In other words, when things grow, we don't make the atoms. There's not new atoms being made when new animals are born. When a new plant grows up out of the soil, it's not making new atoms, okay? It's just recycling old atoms, repositioning them, repurposing them, okay? So, how do we get a view of atoms, right? I said they're much smaller than visible light, okay? And that would be the wavelength of visible light. Ideas we'll get to later. But suffice to say, they are too small to be seen with visible light, all right? Well, as chains of individual thorium atoms in the 1970 electron microscope or micrograph image, okay? So here we're seeing individual atoms showing up in this graph using something called an electron micrograph. We're using the wavelength of electrons to see things smaller than the wavelength of light, okay? Again, an idea that you don't need to understand currently. They've been revealed as ripples in rings by scanning tunneling microscopes in the mid-1980s, all right? And the classical model has a nucleus at the center surrounded by electrons, okay? And the modern model also has a nucleus at the center surrounded by electrons. It's just the way in which the electrons surround that nucleus has changed as our understanding has improved, okay? But regardless, we can see atoms in actual structures, rings, chains, and so on. All right, so we really have an idea of the structures they form, and they truly do take form as they position themselves relative to other atoms. Okay, so, but what about an individual atom? A more accurate view than the cartoon picture from 2 slides ago. Well, there is a nucleus. It's a concentration of nearly all the mass, okay? So we're talking about more than 99% of the mass is in the nucleus of the atom. Okay? It would actually be more, it'd be more than about 99.9%, because I think the proton is about 1,400 times more massive than the electron. And the neutron is slightly more massive still, but only slightly. Okay? Nucleons are the building blocks of the nucleus, where all the mass is located. All right? So they all are identical, all nucleons, but with one difference. They can have a neutral state or a positive state. Okay? But otherwise, they are really have more in common than they differ. Okay? And the neutral state of the nucleon is the neutron. And the positive state of a nucleon is called a proton. Positive charges repel positive charges and attract negative charges. So the nucleus is full of positive charges. So you might have a good question, and you should. How does the nucleus hold itself together if it's full of a bunch of positive charges that want to tear itself apart? Now, it's not a question we're going to answer today. We can't answer every question in every lecture. Okay? Quarks, which I mentioned briefly before, are the particles that make up nucleons. And there's different combinations of quarks that can make up the nucleons, both neutrons and protons. All right, and quarks are quite complicated than the different types of quarks. So suffice to say, there's just quarks are the building blocks of nucleons outside the scope of the class. Okay, so atoms, they refer to the particles that make up a substance. But there's another term we're going to be using quite a bit, which is an element or an elemental substance. Well, an elemental substance is composed of only one kind of atom. Okay? So the lightest and most abundant is hydrogen. So pure hydrogen would be an elemental substance because it is not a mix nor a compound, terms we'll define in just a minute. Okay? To date, there are about 115 known elemental substances. 90 occur in nature, and the others are produced in the laboratory and are very unstable and might only exist for a millionth or a billionth of a second before they disappear. The words atom and element can be used interchangeably, but an elemental substance is referring to more than one of an element. Okay? And obviously, if we're talking about 115 elemental substances, what we're talking about is the periodic table. Okay? Which I'll show in just a minute. All right? So the elements, well, they're the building blocks. So the composition of living things include these elements: oxygen, carbon, hydrogen, nitrogen, and calcium. All right, so we have these key elements for life as we know it. The periodic table is a chart, it's the chemist's roadmap of elements arranged by their atomic number. It's one of the key terms we want to make sure we understand. Okay? And the atomic number is the number of protons, not the number of neutrons, nor the number of nucleons. Instead, the atomic number is specifically the number of protons. All right? And the way the periodic table is set up is it's arranged from left to right, each having one more proton and electron than the preceding element. On the far right, outer shells are filled to capacity, known as noble gases. All right? Because it turns out that electrons orient themselves in something we call shells, but that are not literally shells. Okay? So here is the periodic table. Let's take a minute to appreciate it. If we look here, as the previous slide said, we read from left to right with this element, hydrogen, having an atomic number of 1. That means it has 1 proton. Helium has an atomic number of 2. That means it has 2 protons. Okay? Now I'll talk more about this in just a minute, but notice underneath the name hydrogen is this number 1.0079. That is the atomic mass. Okay, the number on the top is the atomic number, but the lower number which is a decimal, is the atomic mass. The atomic mass is approximately the number of nucleons. The fact that it's not integers, like the atomic number, is kind of immaterial to this class. It has to do with the binding energy of the nucleus, which is very important for things like fission and fusion, but not something we have to worry ourselves about. But we will talk about binding energy, and it's where some elements have different amounts of binding energy. But we won't talk about that until we talk about fission and fusion specifically as sources of energy. Okay, which again is a much later chapter. You can see there's kind of a common theme. A lot of these ideas we'll come back to in the modern physics chapter. Here we're just kind of doing a survey, as I said, of chemistry, not modern physics. Okay. But regardless, the atomic mass is approximately the number of nucleons. And I'll say this again. And so then hydrogen only has one nucleon. So that means that hydrogen actually doesn't have a neutron. A typical hydrogen atom is just a single proton and a single electron. Now, when we talk about isotopes, you'll learn that that would be, in most intents and purposes, considered an isotope. But we generally use that term, which I'll repeat again in just a minute, as a term for the less common forms of a particular element or atom. If the most abundant common form of an atom or element, synonyms, they're synonyms, atom, element are synonyms of each other. I'll use both words interchangeably. So if the typical form of an atom is called an isotope, then you probably are misusing the term isotope. You might as well just call the most common form the atom, or that element. In this case, hydrogen, an element, has an atomic mass of 1.0079. That means a typical element of hydrogen only has a proton and doesn't have a neutron. Are there types of hydrogen that have neutrons? Yes. They even have a special name called deuterium, which means like two, right? Deuterium. Okay? Duo, right? Deuterium. It has two nucleons because it does have a neutron. It's still hydrogen, okay? On the other hand, look at the atomic mass of helium. It is 4. Well, that's more of a typical type of element, where it has an equal number of protons and neutrons. Because if its atomic mass is 4, that means it has 2, because we know it has 2 protons because its atomic number is 2. And then if we take 4 minus 2, then we have 2 leftover nucleons, and there's only one other type of nucleon, which is the neutron. So that's telling us that a typical helium atom has 4 total nucleons, 2 of which are protons, and 2 of which are neutrons. All right? But that's the typical average helium atom. Are there helium atoms that only have 1 neutron? Yes. Are there helium atoms that have 5 neutrons? Yes. They're kind of rare. Certainly 3 is more common, okay? But it's not the most common. The most common is 2, because this atomic mass actually tells us the most common state, okay? As well as telling us a bit about binding energy, okay? So that's key information that you could parse when you look at the periodic table. Those two separate numbers, the atomic mass, the main integer at the top that actually sets the whole pattern of the table, and then the atomic mass, which tells us how many total nucleons there are, okay? So your atomic number, atomic mass, different things. And what does the atomic number tell us? The atomic number tells us only one thing, the number of protons. Okay? So I'm going to repeat a lot of this information on the next couple slides. Okay. So far we've established that the nucleus is most of the mass of the atom. However, the diameter of the outer electrons really is most of the size. Because that nucleus is so small compared to the diameter of the outer electrons. Okay? That diameter is determined by the amount of electrical charge in the nucleus, and it gradually decreases from left to right across the periodic table. Right? So as we get to the right, the diameter is tighter, smaller. Okay? As nuclear charge increases and electrons are added to the outer orbits, the inner orbits shrink. They become more packed in. All right? The structure of those orbiting electrons changes. So obviously I focus on the nucleus a lot, but the electrons are of key importance. Okay? This is showing the relative size of atoms based on their electron shell as seen on the periodic table, following the trends that were established on the previous slide. This is not showing the nucleus of any of these atoms. The nucleus would be tiny within that shell. All right? About 100 times smaller. It would just be a single little pixel, if that, within each cell. Okay, each shell. Now, two very important terms, which I've introduced, the term isotope. The other I haven't mentioned much, but I've been setting the stage for it. Ions and isotopes. Okay? So an ion is a charged atom. Positive ions have a deficiency of electrons. They're missing electrons. Negative ions have an excess of electrons. Okay? So a typical atom, that's one that would not be called an ion, has electrons equal to protons. Okay, so that's always your baseline assumption. If you look at an element, if you look at helium, how many protons does helium have? Well, the atomic number is 2, thus the number of protons is 2. So how many electrons does helium have? 2. Okay, so it's always an equal number. Now, is it possible to lose or gain electrons? Yes, that's what ions are. They lose or gain electrons based on particular processes that can cause that to happen. Okay, perhaps outside energy. Okay, perhaps bonding chemically with other atoms. Okay, now that's an ion. An ion is a change in electrons. An isotope, however, is a change in neutrons. So an isotope are atoms of the same element with different numbers of neutrons. They have identical behavior. Why is that? Because the behavior, and by behavior I mean chemical behavior, is set by electrons. Because the electrons are on the outside. They're 1,000 times bigger than the tiny little nucleus. The way the electrons interact with other electrons of other atoms really defines everything that atom is going to do. So the electrons set the chemical behavior. So then if you're just changing the number of neutrons, you're not changing the chemical behavior. You are changing the mass, so that's important, but you're not changing the chemical behavior of that atom. Okay? So both isotopes and ions are the same element. Okay? So I could have an ion of helium. I could have an isotope of helium. It would still be helium. So neither of them change the element. In fact, if you haven't noticed, the only way to change an element is to change the number of protons. Okay? So more about isotopes. Protons in the nucleus matches electrons around the nucleus, but not necessarily neutrons. Okay? Now, when I say match, I mean, can you still have an ion? Yes. But in a non-charged state, you can always assume that the electrons matches the number of protons. But neutrons you can have a totally resting, just average atom that might have a lot extra neutrons, or think hydrogen, not even have a neutron at all. So that idea that neutrons can be fundamentally different than protons, where electrons can't unless there's outside energy, is an important difference between the two. Okay? Ions and isotopes don't share that much in common. Although on the one hand you can say, oh, one is just varying electrons, and the other idea is just varying neutrons. They have fundamentally different meanings and consequences. Okay? So, isotopes, atoms of the same element with different numbers of neutrons. Identical behavior, because the behavior is set by the electrons. And by behavior, we mean chemical behavior. They're identified by their mass number. Think what I was saying on the slide with the periodic table. The mass number is the total number of protons and neutrons in the nucleus, or number of nucleons. Example, iron isotope with 26 protons contains 30 neutrons. The mass number is 56 because it is the sum of 26 and 30. Thus, it is referred to as iron 56. So I made a big deal about how hydrogen is missing one nucleon. What the heck's going on with iron, right? Iron has 4 extra neutrons. Is that weird? And is there iron that doesn't have 4 extra neutrons? Yeah. You could have iron 54. You could even have iron 52, okay, which would be an equal number of protons and neutrons. But iron 52 would be very exotic, very rare, because it turns out that as you get to heavier and heavier elements, including iron, which isn't particularly heavy, but is on kind of the tipping point of the so-called heavier elements, you will actually almost always find, sometimes really, truly always find, more neutrons than protons. Because it turns out there is a stability concern for the nucleus that means that physically it ends up having more neutrons in order to be stable. Okay? But of course, the biggest atoms are never stable. They're always radioactive. They're just too big to be stable, even with those extra neutrons. Okay, so let's do a check here. The atomic number of an element matches the number of what? The atomic number, not the atomic mass. Make sure you got this, okay? It is both the number of protons and the number of electrons, okay? Is it the number of neutrons? Absolutely not, okay? Absolutely not. A nucleus with an atomic number of 44 and a mass number of 100 must have what? Okay, think about this. Mass number of 100, atomic number of 44. And what does that mean? 56 neutrons, because there are 100 nucleons and 44 protons, right? Because atomic number is number of protons. Okay, that's it. That was our crash course in the basics of chemistry, and really, really the basics, right? We're not going to do more chemistry. This is a physics class, okay? But you are responsible for those terms and understanding the difference between atomic number and atomic mass. Let's wrap this up with a few more definitions. Compounds and mixtures. What's the difference, okay? Well, when atoms of different elements bond to one another, they make a compound, okay? So a compound is different from the elements from which it is made. It behaves chemically in a unique way, and it can only be separated into its constituent elements by chemical means, okay? So it would require some sort of actual chemical process, a reaction with something else. It would require an input of energy in many cases. Example, salt is a compound of sodium and chlorine, all right? So they are chemically bonded to each other. On the other hand, a substance that is mixed together without chemical bonding is called a mixture. Air is a mixture. It is composed of different gases, say for example, nitrogen and oxygen. Well, both the nitrogen and oxygen in the mixture that we call air are themselves molecules. They're actually diatomic molecules, O2 and N2. And of course, there's other molecules in the air as well. But then those molecules aren't bonded to each other. So the nitrogen and oxygen aren't bonded to each other. They exist as separate molecules in the air. Okay? That's why it's a mixture. It's not a compound. So a compound is the substance, but the particle, the indivisible piece of a compound is the molecule. So in the same way that an elemental substance is formed of elements, a compound is formed of molecules. Okay? And a molecule is simply 2 or more atoms bonded together. Example, ammonia, NH3, where 3 atoms of hydrogen and 1 atom of nitrogen bond together. All right? This one right here. That's ammonia. Right, here's some other common molecules, including H2O over here, water. Okay, this is the diatomic oxygen I was talking about. That's the way you're going to find oxygen in the air. But it won't create a new molecule of nitrogen. It's just going to be coexisting as a mixture with nitrogen, another common element in the air. Okay? So, chemical reactions, a process in which atoms rearrange to form different molecules. That's what that means. Okay, chemical reactions aren't about changing the atoms themselves. They're just about atoms joining up together to make molecules. Examples: pulling molecules apart requires energy. During photosynthesis, sunlight's energy breaks the bonds of CO2 to produce O2 and carbon. Combining atoms releases energy. Oxygen atoms combine with iron atoms to form rust. Okay, so that means that combination of many elements is energetically favorable. All right, so that's why rust kind of forms on its own. You don't have to have an input of energy to form rust. Rust actually is going to happen in output energy. Whereas, the idea of photosynthesis requires sunlight. It requires an input of energy. Are there examples of breaking bonds that release energy? There are, right? So not all breaking bonds really require energy, but most do. Okay. All right. More definitions. Okay. We're just going to do a couple of quick modern definitions. Since we're talking about matter, we might as well talk about the big pictures about matter. And some of these ideas we won't actually return to in later chapters because we do some fun modern physics, but some things we don't do because we maybe leave it for an astronomy class. So this might be the only time you're really going to see antimatter and dark matter in this class. And we're not going to say much about it. It's just going to be, but it's fun to acknowledge. Okay, so what is antimatter? Well, matter is composed of atoms with positive nuclei and negative electrons. Okay, right? So positive protons, negative electrons. Antimatter is composed of atoms with negative nuclei and positive electrons. Positive electrons, by the way, are called positrons. This might sound like something that's made up in like a superhero movie, but it's real, okay? Positrons do exist. They're created in lots of reactions, usually high energy reactions, but they're created in abundance in our sun, for example. They can be created fairly easily in a laboratory, okay? However, both matter and antimatter cannot exist in our environment. Whenever a positron and, so here this is a positron, right? Whenever a positron and an electron coexist, they annihilate each other. They cease to exist, both of them, and pure energy is produced in the form of light. All right, but the matter is gone completely. Both the positron and electron are completely gone. They are turned into light, okay? By E equals mc squared, something we will talk about in a later chapter, called special relativity, okay? So, because there's so many electrons in the universe, positrons don't stand a chance. It's not going to take long until they find an electron, a stray electron, somewhere in the environment, interact with it, and get annihilated. It's very hard to confine positrons in an environment without any electrons. Is it possible? Yes. In fact, there's essentially magnetic fields inside of chambers in the biggest supercolliders, these sort of experimental facilities where scientists crash particles together to create new particles, and in the process create antimatter, where they're actually collecting substantial amounts of antimatter. And by substantial, I mean nanograms of antimatter, but more antimatter than that's ever been collected in one place at a time. Okay? All right. So, a little bit more about antimatter. Positrons have the same mass as an electron, but are positively charged. That's a common form of antimatter. The other type of common antimatter is antiprotons, which have the same mass as a proton, much more massive, but are negatively charged. Okay? All right, so that's antimatter. It's made up of protons and neutrons, essentially, right? It's very similar to normal matter. It's just the charges are reversed, and it tends or almost always will be annihilated right away, but commonly produced. And we understand it, okay? We like I said, there's magnetic fields in chambers that actually are trapping and holding onto the stuff in facilities. But you know what we don't have any samples of, and we're not even sure if it actually exists, is something called dark matter, okay? Dark matter has never been directly experimentally measured, but we see a lot of indirect evidence of it. What is it? Okay? It is unseen and unidentified matter, very different from the elements that comprise about 23% of the matter of the universe. Okay? So dark matter forms about 23% of the universe. All right? We'll talk about how much ordinary matter composes in just a second. But what the heck is dark matter? We're not sure. What we do know and why it's called dark matter is that it does not interact with light. All right? And that's a big thing about matter, is that think about ordinary matter, including antimatter, because antimatter is ordinary matter. Okay? Well, antimatter and ordinary matter, when they collide, when a positron hits an electron, what is produced? Light. Well, that's clearly an interaction with light. Furthermore, if you put light into an atom, you can excite the electrons in that atom so much that the electrons get bounced out of the atom, and you've produced an ion. In fact, a plasma is an ionized gas, where all of the elements in that gas are so excited that all their electrons are gone. Okay, they've stripped the electrons away in a high energy state. There's so many examples of atoms interacting with light. The very mechanism that allows a window to be transparent is atoms interacting with light. All right? But apparently, a huge chunk of the universe, especially in giant clouds surrounding galaxies, there's matter, which has mass, so it interacts with gravity, but it doesn't interact with light. And we have no idea what it is, and we've never directly measured it. We've never trapped antimatter, not antimatter. We've never trapped dark matter. We've never created dark matter. We don't know what it is. There's a lot of theories, but no confirmed evidence to back up any of those theories. Okay? So, that's dark matter. Based on our calculations of galactic motion of the universe, we think it composes, as I said, 23% of the matter in the universe. Even weirder, there's something called dark energy. It is an anti-gravity energy that comprises 73% of the universe. So whereas dark matter interacts with gravity, but not light, there's apparently something else that is permeating the universe that opposes gravity and makes up most of the energy-matter continuum that is the universe at a whopping 73%. So if you think about that then, dark matter and dark energy would form 73 plus 23, which is 96% of the universe. That means that ordinary matter, including antimatter, but again, remember antimatter doesn't last very long, ordinary matter only makes up about 4% of the universe. All the stars, the planets, the dust, us, all the gas that makes up our atmosphere, all of that is only 4% of the universe. That's hard to swallow, right? That's unbelievable. Finding the nature of dark matter and the nature of the energy of empty space are high priority quests in these times. What we will have learned by 2050 will likely dwarf all that we have ever known. So what's actually neat about the culmination of this lecture, that obviously mostly focus on just making sure you understand the difference between atomic number and atomic mass, is that, yeah, dark matter and dark energy are truly the forefronts of modern physics, but at the same time, not the only forefronts of modern physics. It's amazing stuff. All right, well, we'll wrap it up there. Thank you so much for watching this video on Chapter 11, An Introduction to Matter.